Okay, so hello everyone again after the holidays. I hope you have rested well. Meanwhile, until everybody is connecting, so if you have any questions, you can ask. I'm here to help you. Just tell me if you can hear me well, okay? So I will know that everything's fine. How will we have final exam? That's a good question. I don't know yet. But I think it will be held online, but you will receive questions, I guess. I have to discuss this with Thomas, but I think that we will post questions and you will have a limited time to answer them. Or it will be organized in Moodle. I have never done that. Maybe you will have to submit answers to the Moodle. So questions will be trickier, of course, because you will be sitting at home with all the material. You will be able to use it. So you will have to calculate something, think a little bit. So it is additional challenge for us to think of some more challenging questions for you to answer, because usually exams were organized in such a way that you would be sitting in a classroom using nothing, so basically limited time, and questions were organized so that they were quite easy actually. So you can do some simple maths or just answer right away. But now we have to rethink that. But I think we will find a way. It will be online, definitely. We can't meet. But it will not be talking to you, I think. It will be something like a test. You will get online, work individually, and answer various questions. Okay, what I wanted to look at, I wanted to see where we are in the schedule. So we are basically in April already. Okay, let me see, I want to have a calendar. Okay, so on 21st, is classification modeling. 21st, okay, this is next week. Okay, so it means next week is a deadline. So today we will have a final lecture on classification. So basically it will include all the tricks on evaluation, how to evaluate classification, what are the metrics, what are the ins and outs, and finally I will give you some hint how to organize your experiment. So basically for your notebook general organization. Okay. Then after, I'm looking a bit further until May 05, until May 5th. So we will have two lectures more. So 2 lectures more will be for the clustering. So I will have to rush because the clustering 2 lectures, okay, I will have to make my best work in order to squeeze everything into the 2 lectures. Then after that, we will have 1, 2, 3, and basically 4, well, 3 lectures for the deep learning. Okay, so 1, 2, 3. I think that we will start right away with the deep learning when in May, on 6th, 13th, 20th. We will be looking into the deep learning explicitly because there's some quite material to cover. And on 27th, it's already passed with final submission. I think that I will talk about, I will give you some additional ideas about various things that we have not covered due to the limited time, various optional topics, I would say, nice to know topics like boosting, bagging, and ensembling methods, and things like that, about the various algorithms that are very popular recently, like XGBoost and things like that, about ins and outs, and etc. I just this is my internal concern, but I wanted to squeeze so much material into the classes, but actually this is not worth doing, because giving too much is not good. We have to find the right balance, and since in this situation we all, including myself, are learning how to do it correctly, in the correct way, so we'll see. Okay, so I guess this answers your question. Answer is basically, I don't know. Okay, and let me start showing you guys my whiteboard. I guess that most of you have connected already. Yeah, one guy is still on the side, but that's not a problem, I guess. So I start, recording has been started, that's very good. And I will be sharing my whiteboard. Yes, okay. Let me try to do something about this. Okay, good. I just want to see if you will give me some questions. I want to see the chat box. Okay, I basically inform you that I have a chat box in front of me, so if you have questions, please go ahead and ask throughout the lecture. As well, prepare calculators, because I will be asking you some simple maths. We will be calculating, so I hope that you will be able to do some simple math in order to provide me answers. So have your smartphones with your calculators on, or computers. Okay, so we will go into the evaluation of the classification tasks. So classification. Okay, I have to get used again in using this board. Evaluation. Okay, so basically we will look into various metrics and how to interpret them. I think some of you have the microphone on. It might be disturbing to the others, unless you want to ask something. Okay, so basically we are, for each input vector x, we are predicting y, which is coming from the categorical values, right? So basically what we are doing, we try to make sure that our y, the actual class, right? The actual class is equal to y hat. This is a predicted class. Right? So this equality is everything we're looking at. So we want that our predictions were the most accurate, most precise, that everything is fine. So if we are predicting just exactly the same class that we wanted, so this is the best situation we can have. Okay, so in order to evaluate this, what primarily we're looking at once we have a model, right? Once we have a model, so basically this is our classification model, and what we do, we input x vector, right? Xi vector, and it produces the y hat, right? This is the class that it predicts. to be the right class. So what we have here is we basically try to evaluate if it is just the same like with the actual class, right? So this evaluation is what we are looking at, and all the metrics are constructed on this in this respect. So basically the major output for the classification evaluation is so-called the confusion matrix. Confusion matrix, which is constructed so that we have the true classes, so basically Y, right, or true class, like A, so for multi-label problem, right, so this will be, okay, adding one more, A, B, C, and D, these are the true classes, right, that we have in our data set. And these are our predicted classes. Okay, so, okay, just putting like this. And these are our predicted classes. So A, B, C, and D, right? And this is Y hat or predicted, right? This is what we predict. And basically here in these cells, we're putting the number that we expected A and we have got A, right? So let's say this is 10. Expected B and got B, let's say this is 20. Expected C and got C, this is we got, okay, 30. Expected D and got D, 40 items, right? Observations that fall into this. And these, all the other guys from this diagonal, these are errors, right? So maybe we expected B but got A. This was one case, two cases. What we want these to be zeros, right? In an ideal case, these would be zeros. Sometimes they have a lot of observations falling into these cells. So basically, these are diagonals, right? This is okay. This is okay because what we expected is what we've got from our model. All the others are not okay, right? And we have to evaluate this, what's actually happening. Okay, so basically all the metrics with respect to confusion matrix are constructed having in mind the binary classification. So these confusion matrix can be constructed and are constructed for multi-class problems, right? So multi-class problems are possible to construct a confusion matrix, but the metrics that we will be talking about are mostly constructed on the problem of the binary classification. So let's simplify this and let's talk about the binary classification problem. Okay. So let me put again a matrix, but now it will be much simpler. This before it was an illustration that you can do this for the multi-class problems, right? But this is for the binary only, right? So this is binary classification now. Now we are talking about the binary classification. And this is again, this is a true class, and this is predicted. And this one is Y equals 1, and this is Y equals 0, right? And this is Y hat equals 1, and Y hat equals 0. Sometimes in literature, you can see that this matrix is made other way around. So here would be predicted, here would be true. And it doesn't matter, actually. I have seen in literature both ways presented. Here on my table, I actually have 3 books. So quite famous, very good books on machine learning. And 2 books basically show differently. One is the same that what I'm drawing you, where true is on the top and predictions on the left. And other two books are actually on other way around, predicted on top and true on the left. But it doesn't matter. You have to pay attention to that because sometimes these matrices are presented differently. Okay, so basically now notation for each cell. Each cell has its own notation, which is crucial for evaluation of classification modules. So basically, these are so-called true guys. These are true because they do not represent any error. They're okay. And this one is true positive. True positive. Positive because this is 1. Remember, in linear classifier, we have positives and negatives, right? Plus ones and minus ones. So this actually comes from this end. So true positive is where y equals 1. We predict y 1. And this is from the logistic function where we expect that the probability is approaching 1. All right, so this is a true positive. True positives. This is true negatives. True negatives, right? This is cell for true positive. This is cell for true negative. And vice versa. This is for false. And this is for false, right? So these are false. False and false positive. It was negative, right? It was y equals 0, or on negative side in linear classifier, right? But we predict that this is positive. This means that false positive. We have made a mistake and we predicted that this is a positive, but this is a mistake. And these guys are false negatives because they are actually positives, but we predicted them as being negatives. Okay, so basically true positives and true negatives are okay. False positives and false negatives are bad guys, which we want to get rid of. Okay, so basically now we can write it like this, that false positive, this is equal error 1. Error 1, or sometimes in literature this is error type 1. Okay, so this is error type 1. And you can tell that false positives represent that it should not should be zeros, but we predict them as ones, right? And false negatives are the error type 2. This is an error type 2. As an example could be, for instance, we are predicting that y equals 1 is a spam, right? Is a spam email. So we want to minimize false positives that not spam is predicted as spam. So basically this happens in the email systems, that we are waiting for some important email and it just got to be classified as spam. It goes into the spams. So we want to minimize the false positives. So basically by minimizing false positives, we want that none from the non-spam emails would be gone into the spam folder. Or for instance, if we're about to apply, for instance, we have a classifier, then we are predicting a person to be ill with some severe illness, for instance, a cancer, right? And we are about to apply the very aggressive treatment procedure, like for instance, chemotherapy or something like that. So we don't want that the healthy person, right, y equals 0, would actually got this treatment. We don't want to make the person sick because of the treatment itself, right? So that's why we want to minimize the false positives, right? So, okay. And false negatives can be minimized. So as an example, could be here, 1 is equals spam, right? Spam. Or for instance, 1 equals aggressive treatment, right? If we're about to apply aggressive treatment, so we don't want that any healthy person would got into this kind of situation, right? So this is, let's say, this is the reason for minimization, right? Minimization. So we want to get zeros in these cells. in that case, right? Okay. False negatives, error type 2. An example could be, for instance, when a person is actually sick, right? For instance, COVID-19, right? We have this situation right now. So we don't want that people that are sick would be wandering around, going into the shops, etc. So we don't want that our system, our tests that are being used in the testing facilities, right, would not identify sick persons as being not sick, right? So we want all ones to go as ones, right? And so false negative error type 2 would be minimized. So basically, then an example reason for minimization would be 1 equals positive with COVID-19, right? So basically, we don't want anyone who is actually sick to slip through the system. We want it to be identified and isolated and treated properly. Okay, so as well, it could be 1 equals cancer, right? Cancer diagnostics. This is initial primary diagnostics for cancer. So we don't want to slip anyone who has the actual cancer to slip through the further investigation, right? For instance, we have developed a test, and this test is actually very initial, very primarily. So we want that all the guys who are actually have cancer would be tested positive. Then we will be examining them more precisely with some more expensive measures. Okay, so these are the reasons why we might consider minimizing different types of errors instead of just minimize everything, right? Because there are some good reasons for doing so. Okay, so now let's create ourselves an example. So I will put some numbers I just made for myself. So let's put true positives. We have 100. False positives we have 10. False negatives we have 5. And true negatives we have, let's say, 50. Okay, let's say we have 50. Okay, so basically in our data set, we have a situation that we have y equals 1 is 105, because this is 100 plus 5. This is 105 cases, right? 105 cases, y equals 1. This is the class, and these are number of observations. 10 plus 50, this is 60. So this basically indicates that our data set is not correctly balanced, right? It's not balanced, right? We will be exploring this later on, but this is not balanced data set, right? So classes, they do not represent it in the same way, right? Because we have 105 and we have 60. Okay, so now we have predicted y equals 1 as 110 cases, and we have predicted as being negative, right? This is 55 cases. Okay, and in total we can sum up these guys or sum up these guys. We have 165, and this is our n, right? So basically, this is our data set. Okay, we just made up a small case. For instance, we have a classifier, we have a model, and this model on 165 cases has produced this kind of the confusion matrix, right? So now let's go through the various metrics. Okay, so one of the obvious metrics and most often used, sometimes it is used just that metric, is so-called accuracy. Accuracy. And this metric basically answers the question, how often we get the correct class. How often class is correct. Right? So how often the class we predict is actually correct class, right? So what we will be using ACC, right? ACC. So how to calculate that? This is easy. We have true positive plus true negative, right? So all okay, guys? All okay, guys, divided by n over all cases, right? So what we do, we basically have 100 plus 50, okay, and divided by 165, and that gives us 0.91. Okay, so our performance in accuracy for accuracy metrics is actually for the classifier is 91%. Is good or bad? We just don't know. Let's go forward. Okay, another metric, which is for the accuracy, we would like to maximize it, of course. We would like to get 1 here, right? So we always, when we guess, we always correct. But the other metric, this is so-called error or misclassification rate or error rate, all right? Error rate, it answers the question, how often wrong? Wrong, right? So how often we get wrong? So this is an error, right? Error, and it is equal 1 minus accuracy, right? So this is obviously, or we can sum up false positive plus false negative divided by n, and this equal, so basically it equals 10 plus 5 divided by 165. And this gives us, it is easier actually, 1 minus 0.191, right? And it's equal to 0.09. So 9% of the cases, we are wrong. We just get an error. So 9% of all the cases, when we try to classify, we get errors. So this is an error rate. Okay. So now we have to define for ourselves, and you have to communicate when you talk about the performance of your classifier, you have to tell about the baseline. Baseline, right? So baseline, let's call it base. Base, it is actually the random choice. Random choice. So the baseline or the random choice is simply 1 divided by k, and k is the number of classes, right? So if you would be creating a random classifier, if your only input into the project is to actually call the random function and guess it is true or false, 1 or 0, 1 or 0, right? You would be correct. Your baseline, the accuracy would be here for the binary classification case is 1 divided by 2 or 0.5, right? So basically this means that getting 0.5 is a no-brainer, right? So any model, any classifier that performs worse than 0.5 is actually, you did something wrong. You just created a classifier which performs even worse than the random choice, right? So this is the baseline that you have to communicate and you have to understand. The 0.5 is just a random guess for the specific case, right? So comparing the 0.5 to 0.91, 0.91 is much, much better in this case. Okay, so, but having a data set, once you have a data set, you can talk a little bit more. You have a little bit more insight about your baseline. And this additional baseline is called the null error rate, right? Null error rate. So it means how often wrong, right? Okay. How often we would be wrong if we would use or guess a majority class. Majority class, right? So now we will be more wise because we have a data set, and this data set has a majority class. One of the classes is more than the other. So how often we would be wrong? So basically, null error rate is equal 1 minus majority class. So I will write it like this, majority class. So let's make it a number of majority class divided by n, right? And this is equal to 1 minus 105, right? So in our case, the majority class, the more observations we have than y equals 1, right? So 1 is our majority class, 105, and it's divided by n. So n is 165, right? And it is equal 1 minus 0.64, and it's equal 0.36. So basically now, since we have our data set, so no-brainer is not anymore the baseline, which is a random choice, but already the 0.64. Once you have a data set, you can always guess that this is a y equals to 1, right? And if you do so, you would be 64% correct, and your error is 0.36, right? Null error rate. So you would be wrong 1 out of 3 guesses, right? So this is not bad, because if you just always say 1, you just created a classifier which always guesses 1, 1, 1, 1. This is no-brainer. You would be 64% correct. So this is a null error rate, and you have some more insights, right? So basically, 0.91 still much better than 0.64. But basically, this gives you some idea where you have to start from and which number you have to compare with, what you have actually gained in terms of performance. Okay, let's move forward. Now we have additional metrics which are coming mostly from the bioinformatics and medicine. And in medicine and bioinformatics, some measures, like for instance, class equals 1, y equals 1, is much more important. And in medicine, for instance, classes are being not well balanced in many cases. So just like with an example of the aggressive treatment, right? You want to minimize a certain error, or diagnosing the cancer, or diagnosing with COVID-19. You want to minimize a certain cell. So that's why in the metric, which encompasses accuracy, error, baseline, and null error rate, which basically talks about with both errors, right? Which includes both errors, is not always okay. Because for the specific business case, we just want to minimize and concentrate on a certain error type, not both of them. So basically, for that reason, we have some specific metrics coming from medicine mostly. All right, so let's start from the precision. Okay, so precision is a metric which can be expressed like this. When we have 1, right, how often it is correct. So when we guess that we have 1, right, when we guess that we have 1 in this metric, right, when we guess that we have 1, so how often it is correct? When we guess this is that way. Okay, so for illustration of these metrics, let me draw some additional thing because I will not fit there. So for the illustration of these metrics, I will draw some additional here on the side, which I will be adding as we go. Okay, so basically, again, the same matrix, where we have the true classes 0, y hat equals 1, and y hat equals 0. This is true positive, false positive, false negative, and true negative. Okay, so basically precision is when we guess that we have 1, how often it is correct, right? So precision is here. We have precision, which is equal to true positives divided by the guess that it is 1, right? So, okay, I'm just making like that for your convenience. Okay, let me go back here and we will write down the formula now. So precision, again, this is from medicine. We want our first class is the most important one because in medicine it is usually positive diagnosis, for instance, COVID-19, right, which is not desired to have. Okay, so basically precision would be true positives divided by true positive plus false positive. Okay, and in our example case, it will be 100 divided by 110, right? So the precision of our model would be 100 divided by 110, and this gives 0.91. Okay, so this gives 0.91. So the precision of our model is 91%. Okay, so this is basically can be told that this is the proportion of patients that we have diagnosed as sick, for instance, for COVID-19, that are really sick, right? That are really sick. Maybe sometimes we diagnose with the general flu, right? And we just don't want to be this way, right? Maybe we would like to minimize that error type 1, right? Error type 1. So we don't want that patients with the flu diagnosis would be put into the same room where we have COVID diagnosed people lying in. Because most likely after some time we will get this disease anyways, right? Okay, so now let's go into the other matrix. So this matrix is recall. Recall or sensitivity. Or sensitivity or true positive rate. True positive rate. So this, the meaning of that, how often one is predicted. So y equals 1. How often actual sick person was predicted, right? How often actual sick person, this is error type 2 indication, right? Proportion of really sick COVID-19 patients diagnosed. I think this one is more important in this business case, right? So recall, we will be writing like this, rec, right? Recall. This is again true positives, right? True positives and true positives plus false negatives, right? False negatives were ones that have been diagnosed as not sick, but actually they are. And this is a problem for the society, right? So this is a 100 divided by 105, right? So basically 100 divided by 105. Okay, and this gives a 0.95. 0.95. Okay, let me go to this example here. So here we will have the recall down here. Recall, and this is equal to positives divided by y equals 1. Really sick guys, and how many of them we have actually diagnosed? Again, this is in this case of COVID-19 identification, this is the most important to minimize. So basically, for instance, you are creating multiple models for the identification of the patients, and you might choose recall as your metrics, which you will be minimizing, right? So you are generating many models, and you choose the one which has the lowest recall, right? You choose the one which has the lowest recall, because recall is what you are concerned about here. Okay, but usually this is not only a metric that you will be looking after. We will get into this. Okay, now the other metric is so-called specificity. Specificity, right? How often y equals 0 is found correctly, right? How often negatives are actually found okay. Proportion, or we can tell that this is a proportion of not sick persons identified as being not sick, right? So specificity would be equal to true negatives, right? So this is basically true negative with respect to all the negatives, right? So this side of the matrix, okay? True negatives divided by true negatives plus false positives, right? And this equals to, let's go back to 50 divided by 60, right? 50 divided by 60. So 50 divided by 60, and this equals to 0.83. Okay, it's 0.83. And this actually falls into this cell. So this is a specificity, right? Specificity. And we have true negatives divided by y equals 0. Okay. This end, and okay, and one of the last things that I want to say from the matrix directly is so-called the false positive rate, right? Rate of errors, right? So this is a rate of prediction as being diagnosed, right? Errors. So what's the rate of actual our diagnostic errors, right? So false positive rate is equal 1 minus specificity, right? 1 minus specificity, or false positives divided by true negatives plus false positives. Okay, and in this case, it's 1 minus 83. It's equal to 0.17, right? So 17% of the of our patients, right, we have identified not correctly, right, incorrectly. So 17% of, for instance, we have identified COVID-19 patients that have not been sick, that are not really sick. So these unlucky guys would be put into the hospital, into the same room with other ill persons, and eventually we would get the disease, I guess, unfortunately, yeah. Okay. So we can add this false positive rate, right? So false positive rate would be here, false positive rate, right? This is equals to false positive divided by y equals 0. Okay. And obviously we can implement various rates as well. So for instance, false negative rate, right? False negative rate. This is actually what we talked about, that we don't want these to slip in, right? So false negative rate would be false negatives, right? False negatives with respect to y equals 1, right? Y equals 1. Okay. So all these metrics are the major one metrics that you need to understand and need to memorize, because they are being used heavily in many cases throughout the system. Okay. So now to go back to the minimization of errors, right? Now, knowing this, knowing all these metrics, now we will talk about these metrics because we already have defined them here in the class. We can go back into the error, right? So basically, to minimize false positives, right? To minimize false positives, here is a matrix. So minimize false positives, these guys, right? Or minimize the error number one. Error number one, you actually have to seek that the precision would be equal to 1, right? If precision would be equal to 1, you would get the minimization of false positives, right? And in contrary, if you want to minimize false negatives or error type 2, you have to minimize recall. To maximize recall. To maximize recall and get 1 for the recall, right? So these two guys, these two errors need to be minimized, right, in order to minimize these errors. And this actually get into the contradiction, because these two guys are actually have a balance, right? And you need to define which one you would like to minimize actually. So because this is a threshold between these two metrics, we need to define somehow how to use them correctly, right? And for this sake, we have additional metrics which take into consideration both precision and recall. And this metric, which is commonly known as F metric, or let's call it F1, right? And this is an harmonic average of precision and recall, right? So if you want to somehow to leverage, right, and make sure that you have some balance between minimums of false positives and false negatives of both errors, you have to look into the metric which balances these two, right? So in order to, for instance, to minimize false positives, to maximize precision or recall alone, that actually lead to exposure of the other metric, right? So in this sense, we have F metrics which take an average between these two, right? So basically, a harmonic mean, it's not a simple mean, because harmonic mean is stable for the outliers, right? So this is basically stable for outliers and always takes into consideration the lower value. So for instance, if you have, for instance, some value 1, 2, and 3, right? So these values, and you have something like 100. So for the average, average would be somewhere here, the arithmetic average, right? So arithmetic average would be somewhere here, right? And the harmonic average, which is capital H, which is closer to the lower values. Harmonic average is closer to the lower values, right? And even though you would have here, for instance, 200 and 150, this arithmetic average would go closer to these big guys, right? But the harmonic average would stay somewhere here because it actually takes into account the small guys, right? It stays with the small guys. So you can now tell that if you're looking for the average between precision and recall, it always favors the lesser one, the lower one. Okay, so now the formula. F1 equals 2, and this is the harmonic average formula. This is, we have the precision times recall, and this is the sum of precision plus recall. And this metric, F metric, actually goes from 0 until 1, and 0 means bad, 1 means good, as usual for metrics, right? And good. So basically, and you have some value in between, which basically favors both. Okay, so F1 actually comes from the family of F metrics. And these F metrics are constructed so that 1 means that equally important, both precision and recall are equally important, right? Equally important, even though harmonic mean always prefers the lower guys, right? Like here, like I showed you an example. But these two guys are equally important. If regardless which one is lower, it is more important. So F1 goes into this direction anyways, right? So let's calculate now F1 metric. F1 metric for our toy example, right? 2. We have 2. Okay, you can zoom out. Okay, 2, and now precision 0.91 and recall 0.95, right? 0.91 times 0.95 and 0.91 plus 0.95. Okay, so can you calculate that for me? Type it down into the chat box, the answer. If you're not sleeping, hopefully you're not. This is just to make sure if anybody is awake. Okay, we have a winner, Jonas. Cool. This was not the contest, but anyway. So 0.93. Okay, cool. 0.93. This is the F1, which takes a balance between the two, right? So basically, we have between 91 and 95. We have 0.93. That's good. Okay, let me see. Okay. So F1 and 1 is actually means that both are equally important. And for the harmonic mean, there is a generic formula for the not so equally balanced F scores. So the generic formula for F scores is constructed this way, that we have F and beta, right? And beta is actually the balance between the two, equals 1 plus beta squared, right? And now we have, again, precision times recall. And here we have beta squared times precision plus recall. What it does, since this number is multiplied by the precision, so this number actually tells the importance of the one parameter in case of the other, right? So if we have beta more than 1, right? So it basically rises this part. So then recall is more important. This means that recall is more important because this guy multiplied by some number which is more than 1, right? It basically minimizes this guy. So for instance, the commonly used metrics for the F-scores, not balanced F-scores, we can tell that there is a F2, for instance, F2, right? So in this case, when we have beta more than 1, then in this case, we have recall more important than the precision, right? Recall is more important than the precision. So basically 1 plus beta squared, right? So this is 5, 1 plus 4, right? And we have a precision times recall. And this is beta squared, this is 4 times precision plus recall. And in our toy case, right, this is 5. And again, you can calculate that. 91 times 0.95. And this is 4 times 0.91 plus 0.95. Again, I expect an answer for you. And in this case, what we have, that recall is more important than the precision. So basically, if you're telling that for this model of COVID-19 diagnosis, recall is more important than the precision. So you have to choose not equally balanced, not F1, but for instance, F2 score, or even F4 score, F5 score. All right, okay, so what's the number here? 2? Can't be. $0.94. Yeah, okay. We have a new winner. Yep. 0.94. Cool. So as you can see, it is higher up and it's closer to the recall, because recall is more important now, right? So 0.95. So it basically climbed up a little bit, right? Okay. So this is frequently used metrics, F1. This one is frequently used as well when we want to raise importance to recall. Let's say it's 2 times, right? Recall is more important. And other frequently used metrics is F0.5, right? 0.5. So now we will have again 1 plus 0.5 squared. This is 1 plus 25, right? 1 plus 0.25, and divided by precision times recall. And here we have 0.25 precision plus recall. And here 1.25, and again, you know the game here. 0.91 times 0.95 and 0.25 times 0.91 plus 0.95. Okay. And again, so what's the value for this? F is 0.5. So in this case, precision is more important, right? We can tell 2 times, right? Precision. This metric is basically telling that precision now is more important than the recall. And now we get 0.92. Thank you, Brendanas. Okay. Cool. So we basically have looked into F-scores, and these are the commonly used F-scores. F1, again, is a balanced, equally important, guys, right? F2 is, we prefer more recall than precision. F0.5, we prefer more precision in case of recall, and beta you can choose. So basically, depending on your task, you can choose beta, which you would like to have here. Okay. Okay, maybe I have to close this notebook and we will go into some examples now. Okay. If you have some questions regarding these, let me know, but I think we will switch gears now and we go into the example. Because what basically mostly describes these things are the examples. If we are giving examples, they are best explained then. Okay, so basically I'm closing this whiteboard. It will be a separate file. Creating a new one. Okay, so now I basically will be giving an example where I will show you that actually the imbalanced data set and various metrics can cause various kinds of problems. Okay, so now let's take an example of this infamous COVID-19. Right, COVID-19 diagnostic model. So we have in our data set, we have 5% of sick patients, right, let's say, and 95% of not sick, right? So basically now, in this case, our baseline, the more advanced baseline, right? The baseline is actually 0.95. So if for all the patients who are approaching, right, we would be getting accuracy 0, right? Accuracy 0, we will be telling that they are not sick, we would be 0.95% correct. Right, so we are basically quite good in terms of the classifier, right? Okay, so the null error rate in this case is equal to 5%, right? So 5%. So we can trick the system that, for instance, if we want to get precision equals 1, what we need to do, right? What we need to do is to identify just one case correctly. If, for instance, we would make a classifier which predicts just one case correctly, we get a precision equals to 1, right? So what happens basically, we just tell that this one is certainly sick for this disease. And if it is, then we get the precision equals to 1, right? Okay. If we want to maximize recall, right, so get 1, so what we need to do, we just basically always predict sick y hat equals 1, right? If we just create a classifier which always predict a sick, so certainly we will catch all the sick guys, right? We will 100% catch all the sick guys. But obviously we would identify them as being sick, and this is not correct. But this is how we can trick the system. So in this case, our system can be very, very good in terms of base accuracy, 95%, right? We can even get the good precision of 1.0 by identifying just one case correctly, or we can get a recall equals to 1.0, then we would predicting always as 1. So this way we can trick the system, right? So now let's say that we will have a free classifiers, free models side by side, so we can look into the examples of various metrics, and you can see how they actually interchange, right? So we take again the same toy classifier. So let's take that, for instance, we always predict sick, right? We always predict sick. So our confusion matrix look like this, right? We get 5 out of 5 correctly, right? And we get 95 predicted as sick, but we are actually not sick. So this is error type 1, and these are zeros, right? And what we will do, we will look into the example where we guess that we're always not sick, right? Everyone is not sick. So our matrix will look like 0, 0, right? 0, 0. We get 5 here. Incorrectly guessed that we are not sick. Type error, error type 2. And this is 95. Is okay, right? 95 is correct. So this is a majority class classifier, right? Because this is a majority class 95. Okay, and let's make an example of something we did. We did a little bit of research, and we have created a classifier which basically does some better job than just we did. And we have 5 here, 5 here, right? Let's take 0 here. So we have not missed any actually sick guy, right? And 25. So this is actually quite a good example, right? So we correctly guessed 5 out of 5, right? So it is all okay. But we just guessed that these 5 guys, these four guys are sick, even though they were not. Okay, so let's now write all the metrics and we will compare them. Okay, so this is what we will write down. This is inaccuracy, error, precision, recall, specificity, the specificity. Now let's write these harmonic one guys, F1, F2, and F0.5. Okay, so I will do this for you because I have it pre-calculated. So now here, the accuracy, since we have 100 items, right? 100 items, so it's easy to calculate. But our accuracy of this kind of model is 0.05, just 5%. Of this model, it is 95%, right? 95%. And this one is again 95 because it's just 5 we have missed, right? 95. So from accuracy point of view, these two models are equal, right? If we just take into the account only accuracy, right? So error is just the difference. 95, 0.05. 0.05. Yeah, so this is just a difference, 1 minus accuracy. Okay, now let's go to the precision. Okay, so for precision, we have 0.05, right? So precision is just 5 out of the 100. So this is not the precise model, right? It just does not identify it correctly once, right? So it always guesses that 1 is the 1. Okay, regarding precision of this model, we have 0, because 0 and 0, we just never guess that this is 1. And this one is 5 out of 10, right? So this is a precision of 0.5, right? 50% precise, this model. Okay, regarding recall, so here we have 1, right? Here we have 1 because we have guessed all the guys that we are correctly identified, right? So recall is 1. Recall is 1. Here, recall is 0 because we have just missed all the ones, right? So recall is 0. Okay, and here recall is again 1. It's quite good model. Okay, specificity. So basically with 0 out of 95, so we have 0. So this is not specific model. This is 95 out of 95. This is very specific model, right? We get 1. And this is 95 out of the 100. This is not 95. This has to be 90. I have made an error. Okay, so I have to delete that guy. Okay, this is 90. 90. Okay. Yeah, 1910. But now it's good. So 90 of 95, this is approximately 0.95. Okay, this is specificity. So now we go to F1. So F1 for that guy is 0.01. This is zeros because we have precision and recall zeros, right? So this is totally bad, right? And this one is 0.67, right? So this is quite a balanced guy, right? Quite good guy. So, okay, so for F2, we have 0.21, right? So it's basically recall tells that recall is more important. So since this is 1 BS 0.05, so it approaches 1, already approaches 1, right? This is 0 again, and this is 0.83. 0.83. Again, recall is more important. Recall precision is 0.50, right? So 83. Okay, and F0.5, which is preferring precision, right? So 0.006, right? So it goes to this direction. Now this one is zeros, and this one is 0.56. Okay. Good. So as you can see, this is an illustration that accuracy might not be a good metric for this model. Not good. And this is important for you to understand that then I've seen a lot of people just reporting accuracy, and accuracy not good metric alone, right? Unless you have a balanced data set. So since this data set is not balanced, right? So not good, not balanced data set, this is not good, right? Because we have situation like that. So much better situation with F1 and F2. So I would guess for this specific model, I would take an F2 as the best metric. But this is my opinion. We can talk it over, right? Best, but this comes from the subject itself, that we want to identify all the SIG guys, right? And we want it to be higher up, and we want to prefer the recall, because recall for this kind of task is more important. Okay, so again, this goes into the contradiction between and into the tension between precision and recall. So basically minimizing error number 1 and error number 2, right? And basically here we go into the situation where we need to choose as well the threshold of the classifier. So usually threshold, then we have a probability, right? Probability that we get 1, then we have the xi, right? So we basically guess the class based on the threshold, right? And the default threshold is equal to 0.5, right? The default threshold 0.5. So basically by changing the threshold, we can get different metrics. So metrics are changed not only on the model itself when you construct a model, but on the choice of the threshold. So let me create now a different example where we basically are choosing the different threshold and we get the different results with respect to the metrics. Okay, so now here is the linear classifier, right, which extends from -infinity to +infinity again. Okay, now here we have x's, right? So x, let's put 3 x's. Now circle, again x, circle, again x, right? And 1, 2, 3. Okay, so this is a symmetric data set where we have 2 classes, right? So basically our classes are from the x's and circles. So we can tell, for instance, x is negative, not sick, right? And the circle is sick, right? So this way we just construct this linear classifier, we put on the line, right? And now we just basically project that line into the some function, right? For instance, function would be like here. Okay, something like that. I don't know if I've missed or not. Maybe I missed a little bit, right? Because I wanted 0.5. Okay, can I undo it? Yeah, I can undo it. Cool. Okay, now I'll try the second time. Maybe now I will do it. Okay, okay, where I want it to be, the difference I want it here, because this is the middle of both classes. Okay, so I basically want to lift it up and turn on this side. Okay, cool. I did it. So this is basically a logit function which we have fitted into our data. So this is probability 1.0, right? And this is the 0. So basically this identifies as being the y predicted equals to circle, and this is y predicted equals to x, right? So this can be, for instance, sick or 1, right? Sick or 1, you can tell, or and this is not sick or 0, right? This is a positive, this is a negative, right? This, because this goes to the -infinity, this goes to the +infinity, and so on. And we have a turn, and this is our threshold. The default threshold goes here, and this is 0.5, and this is the threshold default, right? 0.5. Okay, good. So now again we will have various metrics. I want to show you the metrics. Then we use the default threshold. So then we have a threshold equals to 0.5, right? 0.5. We have a confusion matrix, right? Confusion matrix where ones are 1, 2, 3, 4, right? Basically to this side we have 1, 2, 3, 4 circles, right? And this is a positive class, so true positives are 4, right? These are these circles. True negatives, x's on this side are 4 as well, right? 4 as well, classified. Now we have one error on this side. This is X as an error, and this circle as an error on the other side. So we have error 1 and error 2, right? So once we have taken the threshold equals to 0.5, we have this kind of confusion matrix, right? Okay, so now let's choose a different threshold, right? We will take 2 of them, right? So let's take now with threshold equals to 0.1, right? So let's lower down. So let's be overly optimistic, right? Let's go somewhere here, 0.1. Okay, I wanted it to go here, but anyways, okay, I have to make it more like that. Okay, so basically, let's imagine that this crosses here, right? This crosses here, the function. So now our confusion matrix is different, right? So basically, we will have all ones correctly identified. So 1, 2, 3, 4, 5, right? So basically 5 are correctly identified. And 3 of x's are correctly identified. So negatives are here, correctly identified. Now we have errors. We have 1, 2 identified as being positives on the right-hand side, right? But they are actually negatives, right? So basically here we have to write down 2, and here is a 0, right? Because we don't have circles on the left side. Okay, so we have a different confusion matrix. Now the threshold equals to 0.9, right? Threshold equals to 0.9. I want it to cross over here. So let's put it somewhere right here. So 0.9, and I want it to cross here. Okay. So now we have a slightly different situation. Now all the x's on the left side, so everything's okay with x's. We have 5 here. Now 3 of the circles on the right-hand side, this is okay. These are okay. But 2 circles are on the left-hand side. So basically we have incorrectly classified 2 circles, and this is 0 because no x's on the right-hand side. Okay. Okay, so now basically let's write some metrics. So again, accuracy, precision, recall, or true positive rate. Let's make a specificity. Okay, just a few more. Let's make it a false positive rate, and F1. Okay, that's enough. That's pretty enough. Okay, I will write down what we basically get here, since we have 10 samples, so it's basically simple. So we have 8 correctly identified, so we have 0.8, right? Here 8 correctly as well, 0.8. 8 correctly as well, 0.8, right? Okay. Now the precision is here. We have 5 out of 7. It's 0.71. This I calculated, right? Here is 4 out of 5. So again, 0.8. Here's a 3 out of 0, so this is 1.0, right? Recall, now recall, we have 1.0 for recall because we have 5 out of 5. We have 4 out of 5, so 0.8, right? And we have 3 out of 5, so this is 0.6, right? These are the recalls. So specificities, these are lower hand side, so 0.6, because these are 3 out of 5. This is 4 out of 5, this is 0.8. This is 5 out of 5, this is 1, right? Very, very specific, very nice. False positive rate, this is basically the difference from the specificity. This is 0.4, 1 minus specificity, right? 0.2 and 0. Okay. And F1 score is, I have calculated that, 0.83, 0.8, and 0.75. Okay. So now what we see here, if you look into this, we have changed the threshold, right? And if you look into this, there is a trade-off between precision and recall, right? This is a trade-off. Because when one is increasing, the other one is decreasing, and vice versa. So what we can do actually is usually we can draw a graph like this, like for instance 1 and 0, right? And basically here the threshold, and the threshold from 0 to 1, right? And this is the default 0.5. What we get, the usual situation is when we go down with the recall, right? Recall goes down. This is a recall. As you can see, we have increased, right? Recall from high up goes down, right? Goes down. Recall goes down. The precision goes up, right? Precision goes up. So this is an illustration of a trade-off between precision and recall. And in order to get a single number, an illustration of this trade-off, usually what data scientists do, they draw a so-called precision recall curve, right? Not in this, like in this example. So you can choose basically from this this example, you can choose the threshold that you can basically satisfy the number of in precision recall, right? So you can basically choose. But what scientists do in order to have the single number metric is they are using the precision recall curve. Precision recall curve. Right, or precision recall curve, PRC, right? PRC curve. And here, what we basically draw is the values of recall here on this axis from 0 to 1. And on this axis, from 0 to 1, we draw precision. Okay, so average would be, the random guess would be on this direction. Whatever recall, we get 0.5 precision. So this is basically the random guess. Random guess, right? Random guess. Or as a single metric, single number metric, PRC is basically area under curve, or AUC, right? AUC. So basically we calculate, we integrate the area under the curve. So for random guess, we basically get the 0.5, right? Area under curve equals to 0.5. Right, so this is a location for the random guess, and the best fit is when we have the curve located over here. Right, so when the curve is located over here, we tell that this is the best fit. Best fit, and obviously, then it goes on this side. We have the area under curve equals to 1. So again, for the PRC area under curve is moving from 0 to 1, the metric, right? 0.5 is the random guess. And this one is the best. This is random. This is bad. All right, this is bad. Okay, so since we have this threshold changed, right, with threshold change, what we can do, we can basically move from left to right. So these are right, this is the right order of the probabilities sorted, right? And we basically can draw the curve, precision recall curve for this situation with the changing threshold. Okay, so let's do it like this. Okay, we have this again, this area. We have here a recall. Here is our precision, right? Recall and precision. We have from 0 to 1, from 0 to 1. Okay, so now when we move, right, when we move from lower thresholds from 0.1, we have our recall equals to 1, right? We have our recall equals to 1. And obviously, when we will be moving from here higher up, our precision would be equal to 0. Would be equal to 0 and until 0.721. So basically, in this ordered state, let me take, for instance, the red pen. I will draw the curve now. Come on. Okay, cool. So basically, in the order of increasing probabilities, we're moving up, right? So from 0.1 to 0.2, 0.3, and so on, right? We've been just basically jumping over the samples. We have a recall 1, right? We're moving up, and we move up until 0.721. Then the precision equals to 0.721, right? Precision equals to 0.721, and now it goes like that. Okay, now I take, let me take, okay, I can do this with red ones. Okay. So this is the point of then precision is equal to 0.721 and recall equals to 1, right? So this is 0.71, right? This is the point. The other point is 0.8 and 0.8, both 0.8, right? So basically we can draw somewhere right here, right? And this is right here, 0.8, and this one is 0.8. Okay, and now moving even further, right, in the number of observations, we get to precision equals to 1 and the recall equals to 0.6, right? So somewhere, let's say here, right? So precision 1 and recall 0.6, right? And now, from now on, precision would be equals to 1, right, for all the recalls. So this is the curve. This is the curve for this specific classifier on all the thresholds possible, right? So basically now, if in respectful of what number of threshold, what threshold we choose, right, this is basically the metric that shows how our classifier is doing. So if, for instance, we have 2 classifiers, right, we can compare by using this chart, this plot, right? And now, for instance, now what we can do, we can basically calculate area under curve, right? So let's calculate area under curve. So this is basically 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, Okay, so this guy and this guy. So we can basically integrate these things, okay, and take half of it. So this is something like a 1 minus 0.29, 0.29, because this is the remainder of this guy, right? This is the remainder of this guy. 0.29 is 1 minus 0.721 times 0.2. 0.2 is this one. Okay. So basically this guy, right? This guy. Okay. And we can assume that this one is equal to that one. Okay, so this would be equal something to to multiply these. We're getting 0.058. And so it equals to 0.942. This is not exact, right? Because we would need to calculate this piece divided by 2 and this piece divided by 2 and this piece. So we would get a more exact number. So if you have some desire, you can calculate that afterwards, right? Calculate, all right? But this is, again, this is PRC, area under curve, and this is a single number, which is basically showing that for whatever threshold chosen, this is a metric that displays the performance of the classifier with respect of precision and recall threshold. Okay, so this is one of the metrics. So PRC, area under curve, is one metric that you might consider using for your classifiers. Okay, sorry I'm late, but I have to finish this anyways. All right, I'm just showing lots of examples. Okay, and another example which I have to show is basically the so-called receiver operating characteristic curve. Operating characteristic curve, or basically ROC curve. And with ROC curve, we have a similar situation like just we had with PRC curve, right? We have a box where we match the false positive rate from 0 to 1, right? So false positive rate, we had these guys, 1 minus specificity, right? 1 minus specificity. Okay, false positive rates, these guys. Okay, and we have a precision from 0 to 1 goes like here. Sorry, not precision, true positive rates. I looked into the wrong rates. Come on. Okay, and we have true positive rate. False positive rates vs true positive rates. And again, when false positive rate on all the thresholds is equals to the true positive rate, right? So basically true positive rate equals to false positive rate, right? When this is a random choice. And obviously area under curve is equal to 0.5 because this is equally half of it, right? And the best one is this one, when false positive rate is 0 and true positive rate obviously is 1, right? This is the best, and this is area under curve equals to 1. So again, area on the curve of a ROC curve is changing from 0 to 1, and 1 is best, and this is bad, and this is 0.5 random. Right? Okay. So just like that, let's make this curve for our data set for various thresholds. Right? So we basically take again the box, and this is from 0 to 1. This is a false positive rate, and this is from 0 to 1, and the true positive rate. Okay. So let's take a look. False positive rate and recall, or true positive rate. This is a recall, right? So this is true positive rate or recall via the name, right? Which is maybe more used to you already. Okay. So we have 1. Then false positive rates from 0 to 1, or for other direction, it doesn't matter from which direction you're using. False positive rate 0.4, and this guy is 1, right? 0.2, and this guy is 0.8, and this is 0, and this is 0.6. Okay, so 0, 0.6, we're moving up until 0.6. Again, choice of this. So this is true positive rate 0.6, somewhere here, 0.6, we are moving up, and false positive rate is 0, right? So false positive rate is 0, recall is 0.6. Okay, we just moved up, and now we're moving 0.8, and then the false positive rate 0.2. Right, so here is 0.2, right, somewhere here, and here is 0.8. So we are here. Curve moves like that, right? And now we have 0.4, and recall goes to 1. Right. So here we have a point as well from our classifiers, and this is 0.4. Okay, up like that. Okay, so this is a curve. This is not bad, right? A ROC curve. It's moving like this. It's not perfect, obviously, but it displays some kind of a metric, right? So again, you can put multiple curves here, and you can compare between them, and obviously you can have the ROC area on the curve calculated. So basically we can calculate, this is a half of this guy, right? A half of this guy, and this is 0.4. This is 1 minus 0.4. 0.4 times 0.4, right? This is 0.4 and this is 0.4, right? Times 0.4, right? And this is divided by 2. 16, it's 8, 0.08, so this is 0.92, 92 for our situation, okay? So this is how you can basically compare. Again, this is a metric, very popular metric, which can be used for comparing classifiers among themselves. So ROC LC, area under curve, is again a classifier for your convenience. Okay, let's see. What I have to say. I don't want to waste your time much longer, but I have to show you some examples which are crucial. Not examples, but to say you a few things which are crucial ones. Okay, let's save this now, and I will start a new one. Should not take longer than 15 minutes. Okay. So I guess you have a question. So all this said, what to do with the multi-label classification, right? Multi-label classification. So for multi-label classification, when you have more than 2 classes, all right? So multi-label classification, you can do a few things, right? So basically scores can be calculated in so-called micro scores, micro averaging. You can use micro averaging or micro scores from the individual metrics, right? So basically micro averaging, what it does, for instance, for the precision micro, you take for each class I equals 1 until k, right? For each class, you calculate true positives vs all the other classes, right? So basically you take the true positives from all the other classes, right? So these are true positives for ith class, divided by sum, again, I equals 1 and k, true positives, obviously, if, plus, let me put like here, false positives, if. Right, when you have a multi-label matrix, like this, like I showed you in the beginning, like A, B, C, and A, B, C, right? So the true positives are actually these guys, right, for A class, so A will be equal to 1, 2, and 3, right? 1, 2, and 3. So for the first class, you would take this as a true positive, right? This is your true positive, and all the others are false positives, right? All the others are false positives with respect to the 8th class, right? And so on. So basically you loop over all the classes and you calculate these guys like that. So this kind of aggregation, averaging, micro averaging, takes each observation equal. Each observation regardless of which class it's coming, each observation equal, right? This makes each observation equal. So regardless from which class it is coming, everything is equal. Okay. The other one possibility is to use macro averaging or score, where we basically take, for instance, precision. I'm just showing an example, right? Same for all metrics, right? So same for all metrics. This is precision, just an example. So macro, right? So macro averaging would be just an average of scores, right? So you take basically sum of all 1 until k. You take the precision of the class itself, right? Precision of the class, you just basically calculate for the class, and you divide by k. This is an average. So what this makes each class equal, because you average on the final metrics. That's why it's macro averaging, right? You have calculated and you have made the average of all the metrics pre-calculated, right? PRC area under curve was 0.931. Thank you, Gabius. Very good. Because I just started looking into this calculating and I just noticed that I made an error in my notes, so I didn't want to waste that. Good. Okay, now macro averaging. Okay, so micro averaging and macro averaging, these are two possibilities. There is a possibility of doing the micro averaging, macro averaging, average with weights, weighted with respect to number of observations, right? So you basically can have number of observations and you can multiply by weight. But this is an additional, okay, so I can show it up. So basically precision, macro weighted, for instance, like this could be shown like that. You have sum I equals 1 until k, and you basically take the n of k, number of observations in a class, divided by the number of observations, and then multiply by the precision, right, from this class. Okay, so basically you're taking into account the number of observations in that class, in that specific class. Okay, so these are basically strategies that can be taken in order to calculate the metrics for the multi-label classifiers. So basically for the ROC and PRC curves, curves and AOC, areas on the curve, you can use either the micro average, right, or macro average values, right? So this will give you a single curve, right, for the whole classifier, or you can use a binary output, right? Output. So basically, this would give you times k curves. So you can look into times k curves. So you can create a curve for each class, and you can look into this separately, right? This can be done sometimes, and this is actually being done. This is kind of approach 1 vs all, right? 1 vs all approach. Okay, so now that said, so these are basically ways how to deal with multi-label classification. Closing that up, starting a new whiteboard. Sorry, I'm just making them shorter, these whiteboards. Okay, so now for your homework, you will have to deal with imbalanced data set, right? So imbalanced data sets means that basically what you do, you just create a histogram for yourself, right? For histogram for yourself. So you basically have, for instance, A, B, C classes, right? So this is your classes. And for A, you have that number of observations. For B, you have similar number of observations. And for C, you have very few observations, right? So this is basically means that this magnitude of difference, right? This is number of samples. This is imbalance. And for some of the metrics, this is a very bad thing, right? We already seen some examples where this can mislead, for instance, accuracies and things like that. So there are strategies how to deal with that. So basically, if you encounter this situation, what you can do, and what I would suggest, for instance, in your case specifically, to drop the small class. If you would get into this situation when you have 3 classes and you see that one of the class has very few items, just drop all the items of that class. And you would be doing the binary classifier between A and B. That's very good, right? And it's simplification. You don't need to calculate these multi-label metrics. So basically, I'm writing it down, drop lesser class, right? Classes. This is for your homework only. Because in practice, this is not very good because it's just basically reducing the number of classes. Okay, so in practice, what we are basically doing is doing one of the techniques. So basically, we can do the undersample, one of the techniques, or it might be called a downsample. So basically, from prevalent classes, from A and B, you just take less items, right? You just randomly select number of items that would be equal to C. And this basically would make classes less represented, but they would be balanced, right? So basically you take less, but you balance the classes and they become the same. This strategy is okay when you have enough samples. If, for instance, the lesser class is very, very little, it's just 100 or so items, so it is not worth undersampling the majority classes. So you can take the different strategy. You can oversample or upsample. In literature, you can find this or that. Additional records from lesser class. So basically, this is from rarer class, right? If in a class or classes. So basically, you are taking records few times, right? Randomly, you're selecting records a few times. So here, undersample, downsample was made from prevalent class or classes, right? And here's an oversample. So we basically lift this up. So you sample many times randomly from the C, so that you have the same amount, approximately the same amount of samples, right? A and B. Okay. The other possibility, which is can be used with some algorithms, this is up or down weighting. So basically, some algorithms, even there are modifications of logistic regressions, allow weights to be assigned to the classes, right? So basically, you can assign weights to classes. Usually, the default weight is just 1 divided by k, right? But you can change that. And so the lesser class would gain more weight, or the relevant classes would gain less weight, right? And things like that. Not all of the algorithms actually take that. Some do, some don't. Okay, and the other possibility is basically to generate data. Data generation. So for rarer classes, right? So basically, you can generate some data for the classes that lack samples. And the most popular algorithm which you can find in the scikit-learn is called the synthetic minority oversample. A minority oversample technique, right? And this is, in short, this is SMOTE technique. You can find it in the library, and it basically, you will throw up the data, and it will generate some additional data items. So this is basically something like x1, x2. For instance, you have 2 dimensions, right? And you have lesser class, right, items. So it basically, in between these items, it will generate some additional samples, for instance. This is the newly generated, this is a newly generated, this is a newly generated, right? And you will tell how many you want, and it will generate. And you will see structures like this, pre-generated samples, and this is basically following more or less the KNN algorithm, right? K nearest neighbors algorithm. Okay, so you can basically generate additional classes, additional samples, and you will lift up the rarer class. Okay, so these are the strategies that you might consider for balancing your classes. Okay, so the final word on your practice. So what I would suggest you how to organize your experiment. So basically the experiment would be first item, choose Y, right? Choose the what you will be predicting. And here, once choosing, you will get a multi-label or binary, right? Binary. Choice is yours. You can have the binary classifier. You can always create from multi-label into a binary. Not always, but you can find a way how to group multiple labels into a single one, right? You can find a way. Okay, so basically you've chosen, for instance, you have five wine classes, but you can tell that you can group them. These are expensive wines and these are cheap wines, right? So you will have a binary classifier. And I can tell you upfront that binary classifier is easier, right? So I suggest you to find the binary classification problem. Okay, because even though you have to create an algorithm for yourself. Then identify, choose input vectors, right? Choose variables that you will be using. So in case you will need to create dummy variables, etc., do that. Dummies, right? Whatever, do that. Okay. Now, balance classes, right? Use whatever technique you like, but my suggestion for you, try to balance them, because this way metrics will be much more appropriate. You will not get into the bad problems, right? Now, once you balanced your classes, pick metrics. My guess would be that you are choosing the metric based on the subject. So basically, look into the data you have and think, scratch your head, what would be the worst, right? Error 1 vs error 2, right? Which one you would like to minimize, right? If they are different, if these errors make sense, more sense to minimize error 1 vs error 2, and so on. Just look into your data and try to comprehend that, right? Trying to find a way. Okay. So once you did that, you're ready to go. So you basically split data set into train, valid, validation, and test, all right? Or train and test for k-fold, right? If you are about to use the k-fold method, so you don't need a validation set. Otherwise, you just need it, right? Now iterate, right? So iterate. So build a model. You have a choice, right? Do it yourself. You don't have a choice, right? You have to build one algorithm by yourself. So this will be your model, right? And you then pick some from library, like for instance, logistic regression. You can choose a decision tree. You can choose some other, right? You just choose whatever algorithm you would like, and you create a model. Now, validate by metric. So you've chosen some metric which you think is important for your subject. So you validate that model by using that metric, right? So once you have produced many models, now you basically choose best by metric, right? You can use multiple metrics. You can average. You can think about various ways and methods. Be creative with that. But this is how you basically choose the best model. Now, after you've chosen your best model based on validation metric calculated, now you basically test, evaluate your true error. All right, you find out how your model is actually behaving on the test data set, right? And now a final one, just explore your model, do some error analysis. So basically, error analysis is looking into the confusion matrix, right? So basically, looking into confusion matrix, finding out errors, right? Errors. Then you can go into the samples, right? And find out why these samples were misclassified. Why actually these guys had to be ones, but they were misclassified and gone into the zeros, right? So you can look into this one by one and find some insights and etc. So basically exploring the model, error analysis, this is essential thing that data scientists are doing. We are looking into the confusion matrix, looking into various matrices, right? And finding out why actually some of the inputs were misclassified. Okay, so this is basically the generic plan that I encourage you to follow. For some points, you might not find examples in our notebooks, but you're okay. I think you will find it out in the internet. So like, for instance, class balancing, right, splitting, etc., etc. Most of it you have already. Okay, thank you. I took longer, but this is usually happens with me in these remote lectures. Okay, any questions, guys? Okay, I have to fix this to 0.931 provided by Gabius. Error and save changes. Try again. Microsoft cannot stand 2 hours of lecture. Okay, guys, if there are no questions, thanks for your attention and good luck next week. And try to work on your homework. Bye-bye. Stopping recording.